Okay. I need my pen. Let me get that. So grab a donut if you haven't already. It doesn't seem like there's going to be much turnout for recitation today. Okay, let's get started. So what are we doing? For, I guess, the next 2 weeks or so, we're going to be doing what's on the board right now, which is just differential equations. And so recall from last week, right, what did we do last week? We just solved essentially ordinary differential equations, right? And we solved the homogeneous ones. So in particular, we did like PD of y is equal to 0, or you can think of this as Ly is equal to 0, right? And so how do we do this? Well, we find a basis for the kernel of L, right? And then after we find the basis for kernel of L, we take linear combinations of the basis vectors. Okay, so that's what we did last week. And so what we did was this was essentially the homogeneous solution. Right, so this is essentially a homogeneous ODE. And this time around, we're not going to be doing homogeneous. But this week, and beyond, we're going to be solving PD of y is equal to f of x, where f of x is not equal to 0. Okay, so we're going to be solving differential equations that actually have some kind of meaning now, rather than just the homogeneous types. Okay? And so recall also that your general solution for an ODE was y of x is equal to the particular solution, or the homogeneous solution, yh of x plus yp of x. Okay, so that's where so that's what we did last week, was the homogeneous. This week we're starting to look at what to deal with this f of x on the right-hand side. All right, so the method that we're going to be using today is called the Annihilator Method, or the method of undetermined coefficients. Okay, and this is section 8.3 of your textbook. So what is an annihilator? So you can think of an annihilator as the following. Thank you. So the annihilator essentially is like the reverse kernel. All right, so what does that mean? Well, remember last week when we had like some roots, right? We found the kernel, which was like c times e to the something x, or c times e to the something t. Well, in this case, we're going to give you c times e to the something t, and then you're going to have to find it backwards. So let's do it by example, right? So examples of annihilators. Number one, let's say f of x is equal to cx squared. All right, so what is going to kill cx squared, right? So let's say cx squared is in your kernel. What operator kills it? So I'm going to claim that the annihilator a of d equal to d cubed, all right, is going to be the annihilator that kills this f of x. And note that this f of x literally is the same notation as the f of x up here. And I do that for a reason, is because this is what you do to the right-hand side of a diffie-q. All right, so you know that f of x is equal to cx squared. And I claim that this is an annihilator, right? So let's check. Okay? So d cubed applied to cx squared. What is that equal to? That's equal to the derivative of the derivative of the derivative of cx squared. All right, so I'm applying the d 3 times here. And so what's the derivative of cx squared? Well, that's equal to 2cx. All right, so this evaluates to 2cx. And then the derivative of 2cx evaluates to 2c. Right, and now we take the derivative of 2c, and so that's going to be 0. Okay. Another example, right? Let's say f of x is equal to c times e to the negative 6x. All right. So now I'm going to claim that the annihilator a of d is equal to d plus 6. All right. And let's see if that works. So here's the check. Right. D plus 6 apply to c e to the negative 6x. All right. What happens? Well, let's distribute that d. So this is d times c e to the negative 6x plus 6c e to the negative 6x. All right, so I just distributed the linear operator. And now, what is the derivative of c e to the negative 6x? Negative 6c e to the negative 6x, right? Plus 6c e to the negative 6x. All right, and so these terms cancel. That's 0. And so that's the correct annihilator. Okay, another example. Example 3. Let's say I take f of x is equal to c e to the negative 2x cosine 3x. All right, so this annihilator, I'm going to write it out in a different, I'm going to expand it and then compactify it. So it's equal to d squared, all right, minus 2 times negative 2d plus negative 2 squared plus 3 squared. All right, so a of d, the annihilator, is really d squared plus 4d plus 13. All right, I'm going to save time on this one. I'm not going to actually check it. Just trust me that it's correct, right? And the reason I'm not going to check it is because we're going to have to take like derivatives of this guy, and that involves taking the product rule, all right, over and over and over. So we're going to refrain from that for now. But, okay, what happened? Where's my mouse? All right. Cool. Number 4. All right. Let's say I have f of x is equal to 3e to the negative x plus 2x. Okay. Actually, let's do 3e to the positive x plus 2x. Why not? So just make that a positive sign. Okay, so how do you do annihilators when you have a sum of terms? All right, and the idea is the following. We're going to take the annihilator of each term separately. So what's the annihilator of 3e to the x? Well, we have something that looks really similar above, right, which is c e to the negative 6x, right? So what is a guess then for the annihilator for 3e to the x? D minus 1. Okay, and then 2x, well, what's the annihilator for 2x? Well, we know the annihilator for cx squared is d cubed. So what do you think the annihilator for 2x is going to be? D squared, right? So 2 derivatives on top of 2x will make that 0. So that's going to be d squared. Okay, so the annihilator then, when you have 2 terms added together, is going to be just the multiplication of the 2 annihilators. So this is going to be equal to d squared times d minus 1. Again, you can check that on your own if you want. Yeah?
Is that a 4 on the power?
No, it's a plus x because I had it minus first. Good question. But yeah, I'll just erase it. Then there's no ambiguity. All right, lastly, okay, now let's say I have f of x is equal to c e to the negative 2x cosine 3x. Oh, okay, no, scratch that. I just copied the same thing down. Cx squared e to the x sine 2x. Okay? So what did we do before when we had a sine and a cosine term, right? Well, or a sine or a cosine term. Well, we had this annihilator. So let's just write that down first. A of d is equal to d squared minus 2 times 1 times d plus 1 squared plus 2 squared. Okay, so that's d squared minus 2d plus 5. Okay, so that's what I copied it from up here. Okay, but what does this annihilator take care of? The idea is this annihilator really only gets rid of this part, right? The e to the x sine x part. So we haven't really taken care of the x squared, right? And so how do we do that? Well, to take care of this x squared or to kill that x squared, what we're going to want to do is we're going to take this annihilator and going to raise it to the 2 plus 1 power. All right, so the power on x squared is 2, so that's 2 over there, and we just add 1 to it. So this is going to be d squared minus 2d plus 5 cubed. All right, and again, we're not going to check it because this would take forever, but it's the right annihilator. Okay, so in general then, right, in general, what are my annihilators? So if I have f of x on the left-hand side, then I have some kind of annihilator. Okay, and so let's say my f of x was cx to the k. All right, can anyone guess what the annihilator on that's going to be?
D minus k.
Not quite.
Oh, x.
D to k plus 1. All right, so now let's have cx to the k e to the ax. So we had something almost like this, right, except we didn't have the x to the k term in front. But again, let's take care of the e to the ax term first. How do we get rid of the e to the ax term? D minus a. All right, and now we have to take care of the x to the k term in front, right? And so in order to take care of the x to the k term, we do what we did up here, and we raise that to the k plus 1 power. Okay, and lastly, we have cx to the k e to the ax cosine bx, or cx to the k e to the ax sine bx. So these two have the same annihilator, all right? And when we looked above, you can see why they had the same annihilator. And what is this? Well, you take care of the e to the ax cosine bx part first, and this was the pattern. D squared minus 2ad plus a squared plus b squared. All right, so that part annihilates the e to the ax sine or cosine bx term. And then after we annihilate that term, we have to take care of x to the k. All right, and so how do we take care of x to the k? Well, we raise this to the k plus 1. So if there's no x to the k term, right, you're raising that thing to the 0 plus 1 power, so you're just leaving it as is. Okay, any questions about annihilators before we move on? So we're going to be using this all today, and I guess just for today. All right, so now let's talk about solving non-homogeneous diffie-qs. So it's a 3-step process, all right? Or it's a 4-step process. It's a 4-step process to solving non-homogeneous diffie-qs. How do we do it? So this is applicable to everything, not just what we do today, but what we're going to do in the future. We're going to follow the same 4 steps over and over and over. The first step, without fail, is to solve the homogeneous. So that's either PD of y is equal to 0, or you can call it Ly is equal to 0, right? So we're solving the non-homogeneous diffie-q. PD of y is equal to f of x, right? Or Ly is equal to f of x. And the first step is to set the right-hand side equal to 0. Just do it. Okay? The second step is the following. It's to make an appropriate guess for yp, right? Because the homogeneous, this gets you the YH homogeneous solution. So now we need a guess for yp, okay? And this kind of feels really bad when you start doing it for the first time, because we're literally just guessing solutions, okay? So years of like calculus have taught us like what to guess, but really you kind of just have to guess the right solution. There's like it's just very formulaic, all right? There's really not that much intuition. Okay, so you make an appropriate guess for yp, and there are many methods to do this. All right, today we'll do the Annihilator method. Right, so 8.4, 8.6, no, 8.4, 8.7, 8.8, 8.9, those are all methods of guessing for yp. All right, step 3 is to solve for the unknown constant on yp. So after you've guessed yp, yp is going to come with an unknown constant, and you're always going to be able to solve that unknown constant. All right? If your particular solution has like a C3 in front of it, you're doing it wrong. You should be able to identify what that C3 is. All right, step 4 is to write out the general solution. Y is equal to YH plus YP. Okay, and then the last step comes with, so what's the last step? It's the following. So this is like a part B. Solve for constants with the initial conditions if you're given an initial value problem. Okay, so if you're given initial conditions, you should be able to solve for every single unknown constant in your solution to your diffie-q. All right? If you're not, you should be at least able to solve for the constant on yp. Okay, so let's look at an example then. Okay, so example 1. Y double prime minus 4y is equal to 5e to the negative 3x. All right, and let's throw some initial conditions on there. Y of 0 is equal to 1. Y prime of 0 is equal to is equal to 5. Okay, so we're just going to be doing the 4-step process of solving this diffie-q. All right, step 1, right, is to set up y double prime minus 4y is equal to 0. Right, we want to solve the homogeneous ODE. So how do we do this? Well, this is d squared minus 4 applied to y, r squared minus 4 applied to e to the rt. So you get r plus 2, r minus 2, and you know what your roots are, right? R is equal to plus 2 and minus 2. So this is stuff we saw last week, right? And it was on your midterm. Of course, the right-hand side is always equal to 0, but who cares? Okay, so r is equal to 2 and minus 2. And remember, so now we find a basis for the kernel of L, which is the span of e to the 2t, e to the minus 2t. Okay, and so YH is equal to C1 e to the 2t plus C2 e to the minus 2t. Okay. Step 2. Right, I would recommend going down on your notebook rather than sideways. I just have room. So what is step 2? Step 2, right, is to apply the annihilator to both sides. And then we can obtain a YP guess. All right, so that's why this is called the annihilator method. Because this is what happens, right? We have the equation PD of y is equal to f of x. So if I find the correct annihilator for f of x and I multiply both sides by the annihilator, I have a of d, p of dy is equal to a of d applied to f of x. But what does the annihilator do to f of x? It zeroes it, right? That's the entire point of the annihilator, is to zero out the right-hand side. So this is going to be a of d, p of d of y is equal to 0. Okay? So in our case, right, f of x is equal to 5e to the negative 3x. So what is a of d? Right, so we have that table, or we have this common guess up here, right? We have 5e to the 3x, and so we should probably guess then, or e to the negative 3x, right? So we should guess d plus 3. As the correct guess for our annihilator. Okay, so right, our initial equation was y double prime minus 4y equals 5e to the negative 3x. You don't have to write this. So now you should write this line, right? This was d squared minus 4y is equal to 5e to the minus 3x, right? And what's the next step? Well, the next step was to apply the annihilator to both sides of the equation, right? So now this is d plus 3 applied to d squared minus 4y. And what is the right-hand side always going to be? Zero, right? We annihilated the right-hand side. Okay, so now this is just the homogeneous diffeq, right? And homogeneous differential equations are really easy to solve because we just look at the roots and we just throw them in a linear combination. So now if we solve this, right, this is what, r plus 3, r squared minus 4, e to the rt is equal to 0. And so you get r is equal to negative 3 and negative 2 and 2. Right? So what's your homogeneous solution? Well, cur L is, well, this isn't cur L. This is a cur of A times L. Is now e to the negative 3t, e to the negative 2t, e to the 2t. And so we'll say y then is equal to, all right, c1 e to the 2t plus c2 e to the negative 2t plus c3 e to the negative 3t. All right, so a linear combination of the kernel elements. So we can still see it on the screen. What is that part? That's the homogeneous solution, right? So what must that make the remainder? The particular guess. Okay? So all this work here was essentially, so this is some theory, all this work is essentially to say, hey, this is our particular guess. We're going to guess C3, e to the negative 3t. All right, part 3, right, was to plug y of p back into the original equation to get the unknown constants. So we want to plug yp into the original diff eq and solve for constants. So in this case, right, yp is, well, it's C3 e to the negative 3t, but I don't like carrying like that subscript 3 around all the time on the constant, so let's just give that constant new name. So I'm just say big A, that's the constant, and then e to the negative 3t, right? It's the same thing. All right, so I need to plug this back into y double prime minus 4y is equal to 5 e to the negative 3x. Right, so what do I need? Well, in particular, I need y double prime. Okay, so when I go back to y of p, I need to take derivatives on my particular solution until I get to the second derivative. All right, because that's what I need to plug in back into the equation. So this is yp prime, and so take the derivative of that. That's negative 3a e to the negative 3t. All right, and now yp double prime is 9a e to the negative 3t. Okay, so we feed these equations into that. Okay, so what is yp double prime? Well, we sub that in. That's 9a e to the negative 3t, all right, minus 4 times y, and y was a e to the negative 3t. And so all of this is equal to 5. Oh, no. Okay. So I have my t's and x's. I have t's and x's in the equation. Just have one of them. So notice I had x's up here, and then in my kernel I wrote them as t's. And I think I did that over here too. Okay, so I guess just choose one of them. We're going to make these all t's now. But just be consistent. You either have t's or x's. You don't have both in your solution. I did this last recitation too. So I guess everything is a t. So this equation here, this also needs to be a t. Just to be consistent with everything. Okay. Well, hopefully that's all the t's and x's are consistent now. So this is 5a e to the negative 3t is equal to 5 e to the negative 3t. Okay, and from here I can easily tell what a is, right? I just divide both sides by 5 e to the negative 3t. So big A is equal to 1. Okay, and since big A is equal to 1, I know y of p then is equal to 1 times e to the negative 3t. All right, step 4 is the general solution. So y is equal to yh plus yp. And remember what the homogeneous solution was. That was c1 e to the 2t, or c1 e to the, c1 e to the 2t, plus c2 e to the negative 2t, plus e to the negative 3t. Right? So I have the homogeneous plus the particular solution. And recall, for this problem at least, I also had initial value conditions. Right? So I had y of 0 was equal to 1, and y prime at 0 was equal to 5. Okay, so now I want to solve the initial value conditions for this problem. And so how do I do that? Well, I know what y of 0 is. I can just plug in 0 into this equation right here. Right? And if I do that, I'll get c1 plus c2, all right, e to the 0 is 1. All right, and then plus, right, e to the negative 3 times 0, e to the 0 plus 1 is equal to 1. Okay? And so now I get C1 plus C2 is equal to 0. Okay, so that's one conditions that my C1s and C2s need to satisfy. And now I need to find what y prime of t is. Okay, so I go up to this and take derivatives with respect to t. It's 2c1 e to the 2t plus 2c2 negative minus 2c2 e to the minus 2t minus 3 e to the minus 3t. Okay, now I use my second initial condition, which says that y prime is 0 is equal to 5. Y prime as 0. And so now plug in 0. This is 2c1 minus 2c2, and then minus 3 times 0 is equal to 5. So my second condition is 2c1 minus 2c2 is equal to 8. All right, so now I have two equations, this one and this one, and two unknowns. So I can solve essentially another system, a system of equations, right? And if you do that, you'll get C1 is equal to 2, and C2 is equal to negative 2. Okay, so that's the result of the system of equations with those two equations right there. And now I can write my final y of t is equal to, all right, 2 e to the 2t minus 2 e to the minus 2t plus e to the minus 3t. All right, so there are no unknown constants when I have a system, when I have an initial condition given to me. Any questions? Okay, so pretty mechanical. Just get the annihilator, get your y of p, take some derivatives. Okay, let's take a look at more examples because that's all we're going to do. All right, number 2, y double prime plus 16y is equal to 4 cosine x. Okay, so step 1, okay, is the following. Right, again, step 1 is to find the homogeneous solution, so that's y double prime plus 16y is equal to 0, which is d squared plus 16 applied to y is equal to 0. This is r squared plus 16 e to the rt is equal to 0. R is equal to plus or minus 4i. Okay, so what does that mean? That means that the kernel, okay, so I wrote x, and guess what I also did? I wrote e to the rt. So let's change that to e to the rx. All right, it's really annoying. Like I had problems with this as well, but just like you gotta make sure your x's and t's are the same thing. Okay, so that means the kernel of L is equal to, this is going to be cosine 4x and sine 4x. Right, so now YH is equal to C1 cosine 4x plus C2 sine 4x. All right, part 2. F of x is equal to 4 cosine x. All right, so we need to find an annihilator. And what is an annihilator for this? Anyone?
D squared plus 1.
Yeah, d squared plus 1. All right, so d squared minus 2ad, well, a is 0. And then plus a squared, that's 0, plus b squared plus 1 squared, so d squared plus 1. Okay, now we want to apply a of d to both sides of my operator for the regular equation. So remember, I have 4 y double prime plus 16y equals 4 cosine x. So this is d squared plus 16 applied to y is equal to 4 cosine x. And then d squared plus 1 times d squared plus 16 applied to y. Right? That kills the right-hand side, which is what the annihilator is for. So now I have that kernel that I need to find. So the kernel here, this is the kernel of like a times L, right, is equal to, well, cosine 4x, sine 4x, and then cosine x sine x, right, for d squared plus 1. So y is going to be equal to c1 cosine 4x plus c2 sine 4x plus c3 cosine x plus c4 sine x. All right, and what is these first two terms? Yeah, so that's YH, the homogeneous solution. And that means the remainder, this is going to be my particular solution. That's YP. Okay? So a question I got last time was, why do we need both? And the answer is yes, you do need both, because the kernel of d squared plus 1 is two-dimensional. Okay, so you need both the sine and the cosine term. So yp, all right, again, let's just rewrite it. A cosine x plus b sine x. All right, so yp in your book, I think your book calls it the trial solution, and I think McGrath might do that on the homework as well. So that's what yp is. Okay, so that's your yp, and remember, we're trying to solve y double prime plus 16y is equal to 4 cosine x. So what do I need to do? I need to find y double prime, right? So let's take derivatives. Yp prime is equal to negative a sine x plus b cosine x. And yp double prime is equal to negative a sine x minus negative a cosine x minus b sine x. Okay, so we take these three and we plug them in to original. What do we get? All right, so y double prime is negative a cosine x minus b sine x plus 16 times, and now y is a cosine x plus b sine x. Okay, and that's equal to 4 cosine x, right, on the right-hand side. So simplifying, you got like a 16a cosine x and a negative a cosine x, and then you have like a negative b sine x and a 16b sine x, right? So they just add up, and you should get 15a cosine x plus 15b sine x is equal to 4 cosine x. All right, do we have a sine term on the right-hand side? All right, so what's the constant on b?
0.
Yeah, so the constant on b is 0. And then we can easily find the constant on a, divide both sides by 15 cosine x, and we'll get a is equal to 4/15. Okay. So now, right, our particular solution yp really is just 4/15 cosine x, right? Because we have the constant on a. So this is the A constant, and that goes back in here. And the B constant also goes back into the original YP. So here's YP. All right, step 4, general solution. Y of x, I've managed to avoid the t's this time, is equal to c1 cosine 4x plus c2 sine 4x, right? That's the homogeneous, plus 4/15 cosine x. Any questions? All right, one more. Okay, number 3, y double prime minus 5y prime plus 4y, 5y prime plus 4y is equal to 7x e to the 4x. Okay, so we can streamline this process a lot more now, right? So, for example, finding the homogeneous y double prime minus 5y prime plus 4 equal to 0, we know all we need to do is look for the roots, right? So this is essentially, you'll get like r is equal to, and then you can just like factor this, oops, there's a y there, and you'll get r is equal to 1 and 4, right? So those are the roots of that equation. Okay, so now YH is just then C1 e to the t plus C2 e to the 4t. Right, we're comfortable, or x, e to the 4x. Right, so we're comfortable jumping, right, just finding the roots and then just plugging it in. So these steps, like, you can do all of this. You don't have to say, like, kernel of L is equal to, right? If you can just find the root and then just plug it in, that's fine. Okay, so that's YH. Then step 2, right? So this step, what do we want to do? Well, right, f of x is equal to 7x e to the 4x. So what is the annihilator?
D minus 4 squared.
Yeah, d minus 4 squared. Okay, so again, go back to your table. And everything fits right in. Okay, so annihilator is d minus 4 squared. So if we apply the annihilator to both sides of this equation, right? So this was really d squared minus 5d plus 4 applied to y is equal to 7x e to the 4x. Applying annihilator, so this is d minus 4 squared applied to, and then if you factor this, this was d minus 4, d minus 1, y, and you'll get 0. Right? So this is d minus 4, d minus 1. Okay, but what do I get now? That's d minus 4 cubed, right? Okay, so what are the roots then of this equation? 4 and 1, but how many 4s do we have? Yeah, we have 3 4s, right? So 4, 4, 4, 1. Okay? So what does that mean? That means y is equal to, all right, c1 e to the x, that's fine, plus c2 e to the 4x. All right? But what's after that?
X times A0 times X times e to the 4x.
Yeah, so we'll find some constant, right? C3 times x times e to the 4x. So you need that x now, right? Because of the multiplicity of the root 4. And then, well, we have 3 4s, so we need another one. So this is C4 x squared e to the 4x. But now what? Okay, so what is this first part? This first part is the homogeneous, right? This is YH. So this last part, this is YP. So notice, YP isn't as simple as just solving for, like just factoring d minus 4 squared, right? You actually have to apply it to the original equation. So YP is that. So now part 3, right, is y double prime minus 5y prime plus 4y is equal to, what's the right-hand side? 7x e to the 4x. All right, but your YP is now ax e to the 4x plus bx squared e to the 4x, right? We'll just rename the constants. Right, this is kind of a pain to take the derivative of, but you have to do it. All right, so you have to find yp prime. All right, what is this? This is a log product rule over and over. So this first term, this is end up being a e to the 4x plus 4ax e to the 4x, right? That's the product rule on a. And then you need to take the product rule on b. So what's that going to get you? That's going to get you 2bx e to the 4x plus 4bx squared e to the 4x. Okay, so that's the product rule on b. And we're going to combine these terms just to make the calculation a little simpler. This is 1 plus 4x a e to the 4x plus 2x plus 4x squared e to the 4 b e to the 4x. Okay, so I'm just grouping certain terms, where I'm factoring out an a e to the 4x and I'm factoring out a b e to the 4x. All right, now we need to find yp double prime. Okay, and what is that? Well, take the derivative of the parentheses. That's 4 a e to the 4x. Right, now I add that to 1 plus 4x times 4a e to the 4x. All right, so that's the chain rule on the first term here. And now I got to take the chain rule on the second term. So that's plus, all right, the derivative inside the parentheses is 2 plus 8x times b e to the 4x. And now the derivative, now I add that to 2x plus 4x squared times 4b e to the 4x. Oh, no. Or e to the positive 4x. Right. So it's just a mess. That's all it really is. So at least I took the derivatives, right? So what's the next step? Well, the next step, we're out of time. I wasn't gonna do this anyways. Is you have to plug all of those back in to the original equation. It's a lot of fun and a lot of factoring. So after some cancellations, you'll get that a is equal to negative 7/9 and b is equal to 7/6. Okay, so that means yp is equal to negative 7/9 x e to the 4x plus 7/6 x squared e to the 4x. And then your fourth step is then y is equal to c1 e to the x plus c2 e to the 4x minus 7/9 x e to the 4x plus 7/6 x squared e to the 4x. Okay, so I actually recommend that you try to factor this out because guess what? Something like this will show up on your exam, and you're just going to be you have to just grind through the calculation. So I bite the bullet and maybe do a few of these. And again, this is a multiply, not a minus. Okay, so that's it for this week. Let me hand out homework right now, and then I also have exams. Okay, so homework this week is a lot shorter. if you haven't turned in your recitation homework today, it could turn into me by Friday. I think I said 11 a.m. And okay, so here are the exams. And again, this is where I pretend I know names. Okay, so Anna. Z left. Ian. Tara. Michelle. Bram. Leah. She'd leave. She's here. Felix. Area. Hi, Chen. Okay, should be okay. So a few comments. So I think overall, we feel like the class did like decently well on the exam. I think the average is like a 47, 62. Let's see, what else? I was gonna say something. Yeah, so you might have felt like the exam was very computationally heavy, and that's going to be like the case from here on out. So the idea is then like the final is going to feel like the same way. You're going to feel like you've seen everything before, but it's a matter of like, do I have the time to like actually compute everything? And so, yes, if you haven't realized, now it's like the time to really like get up to speed on like calculating derivatives, because this is going to be the next exam. But then the eigenvalue, eigenvector stuff doesn't go away because they come back with systems of equations. So yeah, so I think it's going to be a lot of computation from here on out. You do need to know like some of the theory. So for example, like number 4 was like kind of a theoretical problem, but it also had a lot of computation. And yeah, in general, that's what what the rest of the exams are going to be like. So they're going to be similar in difficulty to this one. Yeah. Okay. If you have any questions, you can see me during office hours about like how your exam's graded. Again, I only grade like a few problems out of the exam, not the entire thing. So I might have to refer you to someone else. But cool. Oh, take a donut if you haven't already. There's a bunch here.